Listo, ya estamos en vivo.
Okay, gracias. Well, thank you very much for coming to our seminar Tartaglia. Today we're holding our first seminar of the semester, and we're very happy to have Travis Dillon with us. Travis is a second-year student, PhD student at the MIT, yet he had already published several papers in many topics such as combinatorics, number theory, and dynamics. Today, Travis will talk about his recent research on symbolic dynamics. Well, thank you very much, Travis.
Great. Yeah, so I'll share my screen. So where I want to start is just by sort of laying out the world so that everyone knows where we're going to start and some basic background. So setting up like what do I mean what are we going to look at when we're talking about symbolic dynamics? So let's start there. What are the basic objects that we're going to need? And basically there's two things. So we're always going to have a finite set that's usually denoted by script A. This is what's called the alphabet. And then we're going to have another set X, which is some set of bi-infinite sequences with letters from our set A. So what that means is that an element of X is just a sequence that looks like this, indexed by the integers, where each element is inside our set A. Now, these things here, this set of sequences, these are really what we're going to be looking at. If they satisfy certain conditions, then this is called a shift space or subshift. If they satisfy, you can make a sort of dynamical system, and if they satisfy certain dynamical properties, then you can call them this. Now, I don't want to spend too much time on the dynamical background. It won't have that much bearing on what I'm actually going to talk about. So I'm going to align these certain conditions, but you can always think in the background, what's sometimes really driving this is the dynamical considerations that are going on behind. But really, we're just going to look at sets of bi-infinite sequences, and with this knowledge that they're motivated in a certain way, and see what we can say about them. So let me start with just some sort of basic example so I can describe some definitions, but with reference to a specific shift space. So if we have an alphabet that's just two letters, let's say 0 and 1, one shift space that we could define is the set of all sequences that don't have any consecutive ones. Right, so maybe an element of this sequence will look like this, and so on. Right, this is some part of an infinite string that can lie inside X. So this is one way to define it. And it turns out this is in fact a shift space. And one thing that you can be concerned about when you have a shift space is the so-called language of the space, which is just the set of all finite strings, let's say finite sequences that appear in some element of X. Right. So what does it look like for this particular shift space? Well, this is called, we just abbreviate it by L of X for language. We can just sort of go out and calculate this. So which sequences of length 1 can appear in some words somewhere in X. Well, both 0 and 1 can. And what about sequences of length 2? Well, we can tell from this example right here that 0, 0 can appear, so can 0, 1, and so can 1, 0. But obviously 1, 1 can't appear, that's explicitly in the definition. Okay, and then you can go on. So which sequences of length 3 can appear? It turns out there are 5 of them, all of them that don't have 2 consecutive ones, and so on. So you can list it like this. And one thing that it turns out is that the language will define the shift space when it satisfies these dynamical conditions. And so studying the language and studying the space can be a very useful back and forth. In this case, what we can do is we can stratify the language, as I already did, by the length of the words and count them. So there are 2 words in the language of length 1, 3 words in the language of length 3, 5 words in the language of length 3, length 2 and length 3, and so on. And if you go through a little bit of a combinatorial argument, what you'll find is that the number of words in the language that can appear of length n is the n plus 1 Fibonacci number. Now, I mean, this depends on your indexing. Here I'm choosing f of 0 is f of 1 is 1. But they're given by the Fibonacci numbers. So we could, for example, call this shift space the Fibonacci shift. And I'll try to reference this a few times to illustrate another like running examples. So with this example of a shift space in mind, we can start to think about what things we might want to study when we have this. Now, I referenced these certain dynamical conditions. You can think of these spaces as some sort of dynamical system when they satisfy these conditions. And so one thing that you might want to ask is okay, so you define 2 of these shift spaces, when are they basically the same dynamical system? So, when are they equivalent? The corresponding notion of an isomorphism in algebra. This is called conjugacy in symbolic dynamics. So we have this notion that 2 shift spaces let's say X and Y are conjugate if, okay, I'm just going to say they're the same. In some appropriate sense, right? This would involve getting a little bit into the dynamics, but you can think about them as just being you can encode and decode X into Y. So you can recode X and Y to get each other. If you think of these just as sequences, there's some like short finite way to encode X into Y and to encode Y into X, and like bijectively. And so a fundamental question in many areas of math, and including this one, is to be able to tell when 2 different descriptions of this space are really just cryptomorphic. They're, in this case, if they're conjugate. And so what you can do is define various invariants. And well, we've only really defined one quantitative thing, but you might think to try the language as an invariant of the space. Now, obviously, if you're recoding what actually the language is, will change. But you can instead think about like maybe the size of each block. So the number of words of a certain length, or does this stay the same if they're conjugate? Now, it turns out that in general, this is not true. So if you have 2 conjugate shift spaces, the lengths of the allowable words, the number of words of a certain length is not necessarily the same. But you can still extract, it turns out, an invariant from this, which is called the entropy. So even though the number of words doesn't stay the same, the growth rate does. This is called the entropy, and it's h of x for the shift space x. This is, well, first we do a little bit of manipulation of the size of the allowable words. So there's a certain number of words of length n. We take the log of that and multiply by 1 over n, and then take the limit as n goes to infinity. And really what you should think of this is that the entropy is the base of the exponential growth rate of the language. And this is in fact an invariant. So if you have two conjugate shift spaces, then their growth rates will be the same as measured by this quantitative formula. So as an example, if x is this Fibonacci shift, then we know that the number of words of length n is f of n plus 1, which, if I recall correctly, is right. It's got an asymptotic formula. There's some constant, which I think is 1 over root 5. I think this is the right formula, but up to a constant, it certainly is. So we know asymptotically the number of words of each length, and that makes it easy to calculate the entropy. So we've got this limit as n goes to infinity of 1 over n times the log of some constant times 1 plus root 5 over 2 to the n. And what happens is that this limit with the 1 over n and the log will eat the constant, and this just gives you 1 plus root 5 over 2. Right. So really what you're doing is extracting this base of the exponential growth rate, and that's what you get as the entropy. And for this reason, typically this is actually called the golden mean shift, because this quantity of the entropy is the golden mean. Okay, so this is the brief setup. Now I've talked about these things, as I mentioned, more combinatorially than dynamically. But this is some sort of brief motivation for what we're going to talk about. I'm going to specifically talk about the entropy and of a particular class of shift spaces and a new result there. So let's start transitioning to that. One thing that you can do in particular in this and many areas is you can say, okay, so like studying maybe shift space in full generality is a little difficult. Let's define a particular class of them and see what we can say about that. And one of the very popular classes of shift spaces, it's what's called S-gap shifts. So I'll define these, and then I'll give a little bit of a brief comment about why these are a popular class of shift spaces to study. So these shift spaces are defined always on the same alphabet that we've talked before, 0 and 1, and they're defined by some subset of the natural numbers, including 0. So the non-negative integers in the following way. So x of s, this is just the notation for an S-gap shift, is the set of all, as we've mentioned, bi-infinite sequences with this form. And I'm writing it in a little bit of a funny way, because that'll make notation easier later. I'll explain exactly what this means right now. So this notation 0 to the S1 really just means S1 consecutive zeros in a block. It's just an abbreviation for concatenation. So you've got S1 zeros between ones, and then another S2 zeros, and then one, and S3 zeros, and then one, and so on. So it's the set of sequences of this form that satisfy the condition that every block of zeros has length that's inside my defining set S. So really what this is saying is that it's the set of finite sequences wherein between any two consecutive ones, the number of zeros is an element of your defining set S. So this is something you can define. It's parameterized by subsets of natural numbers. So there are many of them. And as an example, if we take S to be the positive integers, so not including 0, then X of S is the set of all sequences where between consecutive ones, there is at least 1 0. Right. And so we've actually already looked at this. What this is saying is that you can't have consecutive, like, two ones without a 0 between them. And so this is actually equal to the golden mean shift. That came up before. So that's a special case of S-gap shifts. Many other like very particular examples are also classes of S-gap shifts. And so I'll mention why anyone really cares about this, right? So certainly you can define it, but why? And there are several reasons. One of them is that S-gap shifts are really nice for explicit calculations. It turns out you can do a lot with them. You can study their dynamical properties. You can study their sort of more combinatorial properties. You can think about how they relate to coding and some other stuff really explicitly. So you can get your hands on these things. And so that makes it good, for example, to give an explicit example of a shift space that has certain properties. So you can write down a shift space that is not Sofic very easily using S-gap shifts and prove that it's not Sofic very easily using S-gap shifts. If the word Sofic means anything to you. And so hand in hand, like they're not just easy to compute, but they also give a lot of varying properties. So they're not trivial. And one of the other reasons is that they have lots of connections. It turns out when you start to actually calculate with them to other areas, so not as surprisingly, perhaps there's some connection to topology and to algebra, but more interestingly, or maybe a little more surprisingly, number theory. And so there's lots that's going on with these things that you can like look at once you actually start to zoom in. But okay, so I've told you that people study this. There are like a good number of papers about these things. And one of the things that you really is typically studied when you start to look at a particular class of shift spaces is what is the entropy. It's one of the easier invariants, like quantitative invariants, to get your hands on. And so in 2007, we actually got a formula for S-gap shifts. This is by Spandl. And it has the following form. So I'm going to write this down because it will be analogous to the new theorem that I'm going to talk about later. So what it says is that the entropy of an S-gap shift that's defined by some subset S is log of lambda inverse. And I need to tell you what this lambda is. So where lambda is a positive number that satisfies the following equation. So I have a sum indexing over all the elements of my set S. So I have what happens is I plug in lambda to this power series given by S, and I get 1. And so there's a unique positive solution to this equation, and that gives you the entropy. Log of the inverse of this is the entropy. So this is the form of the entropy formula. For certain particular cases, you can actually use this to calculate it. For example, you can calculate the entropy of the golden mean shift this way, as well as a good number of others. You can also get a good approximation by just cutting off this series at a particular point, cut off at 1,000 or something, find a solution on your computer, and then this is like a not bad approximation of the entropy. So this is the formula. And after all of the study of S-gap shifts, including this, but and many other things as well, there was some investigation of like maybe some of the things we did here we can extend to limit not just to S-gap shifts, but to some, like you can extend it to larger classes of shift spaces. And as far as I know, the first attempt, at least in the story that I'm telling, was in about 2014. And these are called S prime gap shifts. So you can see even in the name, it sounds very similar. And the idea is that S-gap shifts limit the allowable lengths of blocks of zeros. And so why not extend that to ones as well? These are defined by two sets, S and S prime, which are subsets of the natural numbers, but not including 0. Right, so the positive natural numbers. And it's exactly what I mentioned before. So x of S prime, the shift corresponding to these two spaces, is what happens when you just concatenate blocks of zeros and ones that have the right lengths. So if I were to write it out, one way to write it out is like this. So it's the set of sequences that have this particular form, where Si is an element of S and Si prime is an element of S prime for every value of I. So this is just an extension, and you can see directly that this actually is just an extension of S-gap shifts. So it includes all of S-gap shifts and also some more. And there are a series of papers that studied much of the similar things for S prime gap shifts as there were for S-gap shifts. You can ask many things. Many results transfer with not too much work. Some of them don't. For example, the conjugacy problem within the class of S-gap shifts has been solved, but even for S prime gap shifts, it's not solved. So there's some things that transfer. There are some things that become harder, unsurprisingly. And okay, so there are a series of papers on this, and then the sort of natural question to ask at this point is, okay, so we've done everything that we can do with concatenating blocks of ones and zeros. So what if we just increase the size of the alphabet? And so this was a definition made in 2018, I believe, of so-called S-limited shifts. So these are defined. You just have a little more information that you need to plug in order to get out of shift space. The alphabet here will start at 1 just for convenience. It has, we'll say, Q letters, and then Q corresponding sets. So a set for each letter, each of which is again a subset of the positive integers. That tells you the lengths of the blocks that you're allowed to use when you're constructing strings in the shift space. And when Matson and Statler were defining this, they ran into an issue that it seemed to them there were two possible ways to extend SS prime gap shifts to more letters. So the first one, or I don't know, one of the two is what I'll call ordered S-limited shifts. And so these are defined in the following way. Here I'm just using this notation S underline for the ordered sequence of these sets. So S underline is all of the set information that you're given. Okay, so it's the set of sequences that you can form by taking a block of allowable ones and then a block of allowable twos. Although you keep going until you get to a block of allowable q's. And then you start over at one again. You take a block of allowable ones, maybe of a different length, a block of allowable, an allowable block of twos of a certain length, all the way up to q, and so on, right? So this just has to satisfy the condition that the block of a certain letter is allowed by the prescribing set, right? So each block of ones is controlled, its length is controlled by this set S1 and so on. Okay, so that's the ordered S limited shifts. And if you take q equals 2, then certainly, I mean, up to changing the 1 to 0 and the 2 to 1, you get the same shift space. You just need to rename the letters. But they also thought, okay, well, there's no reason that we really need to order them in this particular way. We could take unordered S limited shifts, where we just take a block of an allowable length and then another block of an allowable length and so on. So here we might write that a little more formally as this. You take a block of a certain length, a second block of another length, a third block of some other length, and so on. And this satisfies a few conditions. So obviously we want these letters to be inside our alphabet. And that sort of goes without saying. And there are two others that we want. So we want the blocks to really say something. We want them to come from the sets. So that's what this condition says. And then we want one more thing, which is that it's just some sort of to prevent any sort of hijinks happening. We want A plus 1 to be genuinely different from A, so that they're an actual block and an actual block of a different thing. And this is an unordered S-cap. The set of all sequences that you can form in this manner is the unordered S-limited shifts, corresponding to the sequence of sets.
Travis?
Yeah.
Yeah, can I ask you a question?
Yeah, sure.
So just to be clear, in the other case,
yeah,
a sequence of, let's say ones, so they have to be followed by a sequence of twos.
Yes, exactly.
Considering that the I don't know, 0 is not in S2, right? On the other and in the other case, in the unordered shifts,
yes,
you can have like you can have a 1 followed by a 3, say.
Yes, exactly. That's okay. The key difference.
But you always that's why you take you don't take 0 in your defining sets, right?
Exactly. Yes.
Okay, fantastic. Yeah, now I get it. Cheers.
So we've got these two different things, and again, in the unordered case, if you take q equals 2, then up to changing the letter names, this is exactly the same as S-prime graph shifts. So these are two different sets. It turns out that neither of them contains the other. So they're sort of genuinely different. And in the paper, this is Matson and Sattler in 2018. They really sort of like studied these in parallel. So they did some stuff for S-limited shifts that were ordered, and then did some stuff for S-limited shifts that were unordered, and did as much as they could with both cases, extending from SS prime graph shifts. And in what I want to focus on, entropy, it turned out that for ordered, let's say the entropy here, for ordered S-limited shifts, the proof really just, they sort of were able to really just transfer the proof from SS prime graph shifts. There wasn't much of a change, most of it was cosmetic. So they were able to get a formula here. But for unordered shifts, something just didn't work out. And it has to do with the fact that how you're building these blocks, like was asked, it can really be sort of random, right? So I could have like a block of ones and then twos and then ones and twos and ones and twos for so long, and then I could throw in a three. But that's not really controlled in any manner, not nearly as much as for ordered shifts. So one of the questions that they asked was, can you get a formula for unordered S-gap shifts, unordered S-limited shifts? And this was the motivation for the result that I'm going to talk about today. And in fact, what I'm going to talk about is a way to solve this problem by generalizing the shift space to something that encompasses both of these classes as special cases. And I think a really nice way to think about it is to think about how we're defining these two spaces. So other than this sort of implicit condition that each of the letters comes from your alphabet, there are really two conditions that we have here. One is a length condition, right? And that appears in both of them. We want the blocks to be restricted by the sets that we choose. And then there's this, this sort of adjacency condition. What blocks can follow other blocks? And it looks like there maybe is not that condition here, but that's because I just wrote it here, right? So the adjacency condition is that ones have to precede twos, twos have to precede threes, and so on. So the adjacency condition is also here. It's just so strict that I can write it on the left-hand side of the set definition instead of the right-hand side. So these are really two different things. And one way, perhaps one very suggestive way that you can organize this information is with a graph. So for the unordered case, and the ordered case, I'll start with the ordered case, actually. I can write down all of the letters in the alphabet. Just write them down, and then I can draw an arrow to indicate which blocks can follow other blocks. So a block of twos can follow a block of ones, like this. And these are the only allowable things, right? Once you write down a block of ones, you know you have to write down a block of twos. But for the unordered case, if I were to draw the same diagram, twos can follow ones, but also ones can follow twos, and anything can follow anything else as long as it's not the same thing. This is why we don't include zeros. We really want to make sure that the blocks are different. So we have these two graphs. On the one side, we have a cycle, a directed cycle. On the other side, we have a directly complete graph. And once you start thinking about it this way, it really seems that these are really just two ends of one spectrum, right? So you can define in this manner of a graph any sort of crazy adjacency condition that you want, not necessarily restricted to these two edge cases, where one is like a minimally irreducible, but like a minimally connected graph, and one of them is sort of a maximally connected graph. You shoved all the edges that you could in. And so this way of thinking is really what led to this new definition that I'm going to talk about of S-graph shifts. And this is like studying S-graph shifts was the paper that this talk is based on. So let's get to the definition here, motivated by this graph picture. So S-graph shifts have much the same information. As I just outlined. So first of all, we have an alphabet, which again, we'll just take for convenience to be the first few natural numbers. And we also have, as before, sets S1 through SQ of the positive integers. And then we need one more thing. We've got G, which is a directed graph with no loops. So a bit of a technicality, but then, so no loops. And its vertex set is this alphabet A. And so really what's happening is we're going to use this graph to define the adjacency conditions. And so what is the set that we're talking about? The shift space, I forget which way I define these in the paper, I think it's GS, is the set of all sequences that you can form in this manner. You take a block of a certain length, take another block of a certain length, a block of a certain length, subject to which conditions? Well, again, we want these to be in the alphabet. We want the lengths to be the right lengths corresponding to the right letter. And then we want the adjacency conditions to be preserved. We want that if AI plus 1 follows AI, then this is really given by an edge in the graph. So this is just a formal way of writing down what I've talked about, of extending this adjacency condition to something that's maybe more exotic. And okay, so certainly, right, like I've taken you down a path of generalizations, and at each step, it's worthwhile to think about, like, is there a reason to generalize? Or I mean, is this just sort of eating itself after a certain point? And SS prime gap shifts were motivated in part by coding theory. I think S limited shifts were a little bit less motivated. It's certainly something you can do. You can maybe argue that you want to see how far these techniques will push. But actually, I think S graph shifts are they're more motivated than S limited shifts. So they contain as particular examples these two things, and therefore also SS prime gap shifts and also S gap shifts. But they also include as special cases. I'll write this as a remark. They include all what's called subshifts of finite type, which I won't define too much. I'll just say that they're basically defined by a finite set of forbidden words. It's something that you can do, but they're pretty important in the study of shift spaces, and they're a very natural class given the sort of dynamical information that I skipped over. So it includes all of these as a special case, and that's already nice. And one of the other really nice things about it is once you start phrasing it in terms of graph theory, you can use techniques from that area to really to analyze these shift spaces. And so it turns out by phrasing these in terms of graph theory and really pulling from that area, we can get a formula for the entropy of all S graph shifts. Whereas if you're just thinking about it in terms of how do you encode the strings, how do you write them down, and so on, it's harder to get it even for the special case of say unordered S limited shifts. So I'll say, as you know, to make sure this motivation is pure, this statement that includes all SFTs is not true for any of the S limited shifts. So it's really the first generalization in which this is true, and it's nice in that manner. So okay, so now at this point, I have finally described to you what the particular shift space that is introduced in this paper, and the question, given the background that I've talked about, is, and also the question from Madsen and Sattler's paper, is there an entropy formula for this whole class of S graph shifts? And the answer is yes, and it has a certain nice resemblance to the entropy formula for S gap shifts that we looked at before. So that's the main result that I want to share. I want to describe this theorem, and then walk through the main points of the proof to see how like we're actually using this graph theory, how we're using some algebra and some combinatorics to actually analyze these shift spaces. Okay. So I'll leave this question up here. And in order to state the theorem, I just need to introduce a very small amount of notation. And then we'll be ready and we can talk about the actual results that are new to this paper. So given an S-graph shift, what we're going to do is we're going to define a certain power series associated to each letter in the alphabet. So for, let's say, if I is inside our alphabet, we're going to put hi of x is this power series. Very simple. You take each of the elements of your set, Si, raise it to the power of that element and add them all together. So this looks very similar to the power series that appeared in Spandl's theorem for the entropy of S-gap shifts. There was a +1. Here there is not. But other than that, this is basically the same formula. And so this is a good way to sort of encapsulate a little more combinatorially as a generating function the information of the set Si. And to incorporate the graph structure, what we define is a matrix. This is a Q by Q matrix. B of x, whose ijth entry, well, there are two cases. So if ij is not an edge in the graph that we're given, remember, so for an S-graph shift, there are two pieces of information. There's the graph and the associated sets. If there's not an edge, then the corresponding entry in that matrix is 0. If there is an edge, then we just put the generated function corresponding to the first letter. So if ij is an edge, then the ijth entry of the matrix is hi of x. Now, you'll notice that this is very, very similar to the adjacency matrix of a graph, right? Where here for the adjacency matrix would be 1 instead of a power series. And indeed, this fact that it's the adjacency matrix, but also we sort of bundled in the information from the associated sets. That's what allows this new matrix, which in the paper we call the generating matrix from generating functions. That's what makes this so powerful and allows us to frame so many results in terms of it. And so as a good example of this, I'll state the entropy theorem for S-graph shifts. So this is a paper that was just published earlier this year. Right, so the entropy of, remember this is the notation for an S-graph shift with graph G and sets S. The first step is that this is log of lambda inverse, which is exactly how the theorem for S-graph shift started. And then I need to tell you how to find lambda. So again, it's a positive number. Such that what? So such that rho of lambda equals 1, where rho is the spectral radius of the generating matrix, right? So I guess in this case it's B lambda. So the point is that, okay, this is a matrix formed of generating functions or power series, if you prefer. And so you can think of it that way, but you can also think of it as, well, if you choose any particular value of x, you plug that in and you get a real valued matrix. And at that point, you can evaluate the spectral radius of that real valued matrix and you get some number. as long as you're within the radius of convergence of all the power series. And so then this gives you a function where you put in a real value x and you get out the spectral radius of this matrix. And you just want to find the value that you can put in that gives you 1. So another part of this theorem, I'll write it in another color, is that lambda exists and is unique. So this is the theorem, and the overall form is very similar to the SGAP formula, where we have this formula up here, subject to lambda being equal to satisfying some equation. And indeed, if you look at specializing S-graph shifts to S-gap shifts, you take this matrix, you look at what its spectral radius is in this particular case, you actually get out the exact same formula, this power series that Spandl had in that case. So it is really like, it specializes all the way down in that manner. Okay, so this is the theorem. This is what I'm aiming to prove for the rest of the talk. So I'll, unless there's any confusion, I'll go ahead and talk about the main points, how you actually go about proving this, to see how this matrix Bx actually comes into the picture. Okay. So what I'll do is I'll proceed in a series of lemmas. There's about 2 lemmas and a big hammer that I'm going to borrow from matrix theory. And then together this will tie into a proof of the entropy formula. So to state the first lemma, I'm just going to abbreviate a little bit. So if W is a walk in the graph, let's say VK, and this is a walk in G, meaning that, you know, Vj is, there's an edge from V1 to V2, from V2 to V3, and so on. Then I'm going to write H sub W of X to be the product from I equals 1 to K of the power series, right? So you imagine walking on this graph, and at each vertex, you pick up the corresponding power series. And if you go past the vertex twice, you pick it up twice. You just keep picking up copies until you end the walk, and you multiply these all together. This is something you can do. It's certainly a definition. And the reason that it's helpful is that it allows us to start to connect the entropy to these generating functions, the H's. So the first lemma that we'll use is that, let's say, if lambda is the radius of convergence for some power series, which don't know. So this is a power series where it's summing over all the walks in the graph. Then the entropy of the shift space is log lambda inverse. So this is, to be clear, some sort of monstrous power series. Not only do we have power series that we're summing over all of the infinitely many walks inside the graph. Like, computing this thing would be a nightmare. But luckily, it's just a stepping stone, and it won't actually appear in the final result. But the point is that we're starting to connect the entropy to these power series. And how do you prove this? This will be partly a sketch. The way that you prove it is to just see what you want to see what this power series is actually calculating. So when I say what is it calculating, I mean, think of it in terms of a generating function. what is the coefficient of x to the n inside this power series. And you can do some calculations. If you know something about generating functions, you can work it out that this is counting the number of words in the language of x. Okay, so where x here, I mean x of gs, and just abbreviating it. This satisfies some conditions. So the length of the word is n. And then also it's composed, or it's built out of what I call full blocks. Which means that it looks maybe something like A1, S1, A2, S2, up through AK, SK, where SI is in the big set S of AI. So it's really built from blocks whose lengths are prescribed, whereas some allowable words, for example, will have a partial prefix and suffix that corresponds to taking like a subword of a bigger word composed of full blocks. So if you want to look at all the words in the language, not all of them look like this, but one way you can construct words in the language is it's built them out of full blocks. That's what this power series counts. That's the motivation for defining these generating functions HI. And I can also define, for comparison, a power series f of x, which also is a generating function, whose coefficient on x to the n is just the total number of words of length n inside the language. And by just comparing the coefficients, we know that at least for positive values of x, the value of this monstrous power series that I defined that's in the statement of the lemma, it has to be at most f of x, just because the coefficient on each coefficient in f of x is at least as big as the coefficient in this first power series. And on the other hand, what you can do is you can account for the prefix and the suffix in each of these words, and using another sort of generating function approach, if you overcount them, you get that you can multiply by this q over 1 minus x squared. And in this case, now each of the coefficients in this second power series is bigger than the coefficient in this f of x, and so it's sandwiched between them. And what does this allow us to do? Well, because all of these power series here diverge if x is bigger than 1, and the radius of convergence of this power series that I'm multiplying by is 1, this tells us that the radius of convergence of this thing in the lemma is the same as the radius of convergence of f of x. And a priori, what I've told you so far, this doesn't help at all. All I've done is define another power series and say the radius of convergence is the same. But the point is that this power series here will be easier to work with. We'll be able to massage it into something nice. This power series is easy to tell the entropy of. And why is that? Well, the radius of convergence of f of x, we know the coefficients explicitly, and we can use the root test. It's ln of x to the minus 1 over n, which if you move the entropy formula around is e to the minus h of x. This just comes from the original formula for entropy. Or what I'll say is that it's not necessarily equal, right? But the limit of this is e to the minus h of x. Then what we say is, okay, but the radius of convergence of the sum over the walks we called lambda, and you rearrange this and you get exactly what we stated in the lemma itself, which is that, well, rearranging the entropy is equal to log of m inverse. Okay. So this is actually very similar to the first step of the proof all the way back to S-gap shifts. This part just sort of copies along because this power series F is easy to find the radius of convergence of, but you want to transfer it to another power series that's easier to manipulate in other ways. And so the key part in this proof, this lemma, is finding the right thing you want to relate it to. In that case, it's this power series. Okay. But the problem with this is that it's a very hard power series to work with, so you want to manipulate it in some way. And so that's where the second step of the proof comes in, which is that the radius of convergence of this series that appeared in the previous lemma is equal to the radius of convergence of another power series, which maybe unfortunately it looks like has two sums, but on the upside has pulled in the generating matrix B of x dn. And I won't go through the proof of this. It's mainly graph theory. The intuition for it is that this is, you'll remember, counting the number of words of a certain length, of a certain form. And the way that you build these words, even without reference to this power series, is by looking at walks on a graph. And if you were to think about not this, but just counting the number of walks on a graph, if A is the adjacency matrix of some graph G, then if you sum over all of the entries in the nth power of A, this is the number of walks of length n. So, this is a little different, but morally, what this part corresponds to is taking walks. And since we're already talking about walks over here, that's the sort of underlying reason why these two things have the same radius of convergence. Now, there's an actual equality between the power series if you add a correction here, term here, but you remove that without changing the radius of convergence, and that makes it a little easier to work with. So that is the second step. And then we have one final step to prove the theorem. And that step really is just sort of appropriating a very, very powerful result in matrix theory. So I'm going to call this a theorem because it is. So this is the so-called Perron-Frobenius theorem. And it finds use also in some other places in symbolic dynamics. It has many, many parts, but I'm just going to state one of them, which is that if A is a square non-negative matrix, meaning just that all of the entries in it are non-negative, then the sum of all of the entries in the nth power of A is more or less the nth power of the spectral radius of A. Now, what it actually, the bound it gives you is a little bit different, but up to polynomial factors, this is true. Up to polynomial factors, the nth power of the radius, of the spectral radius, is an upper and a lower bound for this sum. So that's very nice, because when x is a positive number, b of x is also a non-negative matrix, it's square, so we can use this result. And at this point, proving the theorem is just combining these three parts. So I'll write it out explicitly just to make sure it's all understood. And then we can see how all of these parts come together. So, say, proof of the main theorem. Right, so we know that h of x is log of the inverse of lambda, where lambda is the radius of convergence of, well, if we put the first two lemmas together, we get that it's the radius of convergence of this power series. You sum over n, you sum over I and j, and you look at all of the entries in the nth power of the generating matrix. So this is something. But we know that this is more or less equal to, by Perron-Frobenius, the sum over n of the spectral radius of the matrix to the n, right? So this is just substituting Perron-Frobenius, and this is a very easy thing. We already know that this converges if and only if the spectral radius is less than 1. So its radius of convergence is the value of x that makes it 1. There's some things you might want to check, like, is this function monotonic? Is there actually a solution to rho of x equals 1? And both of these are true. It turns out that rho is a continuous increasing function that goes from 0 to positive infinity. So all of these things are satisfied. But the main idea here is that, well, you really can just compare it to a geometric series, and this is a very easy thing to evaluate. So what this means is that you just need to look for the part where rho of lambda equals 1, and that finishes the proof. I think I don't have enough time to talk about some of the other nice applications of this matrix. You can use it to analyze these shift spaces further. So the two main results that use this matrix are that given any entropy value, I can find you an S-graph shift with that entropy. There's a way to construct it more or less explicitly. And you sort of analyze and see what manipulating the generating matrix does. And then you can transfer that exactly to see, like, you just look at how manipulating the generating matrix changes the spectral radius. And if it doesn't change the spectral radius, then you know you have not changed the entropy, and you can look at how to form a matrix with a particular spectral radius, and this gets you what you want. The other thing is that there's another more powerful invariant called the zeta function, and you can also write a formula for the zeta function in terms of this generating matrix, a determinant involving the generating matrix. And so that's also a very nice result. And it says that this generating matrix is perhaps fundamental to being able to analyze these spaces, which is an exciting idea because this class of spaces is much more general than any of the things that have come before in this story that I've told you. So it's an exciting new tool to be able to analyze these shift spaces. And yeah, that's what I wanted to present today.
Thank you very much for your talk, and I'm pretty sure there are plenty of questions. So if you have no problem, I'd like to know if any of you has some questions.
I have loads.
Great.
I mean, it's more like thanks for the talk. It's really nice. Was really nice. So my questions are more about if you can build certain relationships of this within this family with other families of subshifts.
Okay.
In particular, beta shifts. So just because you mentioned these. Can you go down in your screen?
Yeah.
Up, sorry, just to see when you define things.
Yeah.
Because you define these as prime shifts, right?
Yes.
So there's a paper by Baker and Genchu. It must be from 2015, I think. which relates S-gap shifts with beta shifts, with regular beta shifts.
Okay.
So do you know if there's a relationship between this class, the S prime, with maybe not beta shifts, because I don't know if 0 will be there, but with alpha beta shifts, for instance?
I don't know if that's the case. Sorry. Yeah.
Okay. Okay, that was one question. On the well, you mentioned about, well, all your talk was about talking about how to calculate the entropy, and you mentioned that if any number that you can find an S graph shift with that entropy, right?
Yes.
So do you know if you can use this tool to classify numbers? Say, I don't know, if lambda is a piso number, then the shift that you can build has to satisfy certain property. Have you explored that kind of problem?
I have not. It's a very good question. Because this has come up, I think with S-gap shifts, right? There are various results here. Yeah. So the one question that I have thought about is, so you have an S-gap shift. You can ask not whether just there is one that has a certain entropy, but is there one with few vertices? Because the number of vertices tells you the size of the alphabet.
Okay.
And so given an entropy, say log lambda, in principle, without any other sort of knowledge, maybe you can get it with like the ceiling of lambda number of vertices. This is the best you could hope for. The construction that I make is 2 times the ceiling. So it's pretty close, but maybe you can do better. So like optimizing this value is the only thing that I've thought of, because like, I don't see any particular restriction to why, it shouldn't be able to be lower, but it's an interesting question. Like maybe, so it is true that for any entropy, there are uncountably many non-conjugate shift spaces that have that entropy that are S-graph shifts. So you can't have any of these results that say it's a special type of number if and only if there's like only countably many or something like this. But maybe you could have these sort of results if you restrict also the number of vertices, right? Like maybe like it's a special type of number if you can do it with few vertices or something like this. But I don't actually know any results that specifically say something like this.
Okay, I have another 2 questions. That's the typical people from the seminar know me about, because I always ask this kind of question. So how about the topological properties of this class? I mean, is there a classification whether the S-graph shift is transitive, has specification, is synchronized, stuff like that?
Yeah. So I skipped over all of that here because I wasn't talking about the dynamical properties. There's a whole list of things that do appear in this paper. It's in section 3, I think. And so there's, a lot of this, all of these proofs more or less transfer from all the previous ones. You just have to sort of write out the details. Off the top of my head, I remember there are criteria for mixing specification, some type of almost specification, SFT and SOFIC, that relate to mostly relate to the sets and not to the graph, as long as your graph is like irreducible. But yeah, I think that's the only condition on the graph usually, is that it's irreducible.
Okay. Yeah, and the last one. So you mentioned that this class the S-graph shifts contain all the shifts of finite type, right?
Yeah.
So what about SOFIC shifts?
I forget. I had this question once, and I forget whether I actually worked it out or not. I suspect not. But I don't remember whether this is actually the case or not. So SFTs are fairly easy because you just take the associated set to be 1 for each one, and every SFT is conjugate to a vertex shift. I suspect that the adjacency conditions are too strong to capture every SOFIC shift, but I don't remember whether that's like 100% true.
Okay, thanks. That's well, I hope that I didn't annoy you with that
No,
amount
no,
of
it's
questions.
good.
Cool.
Thank you very much. I don't know if there are some other questions.
Oh, I have another one. Sorry. Yeah.
Great.
The other typical thing. What about the intrinsic? Are they intrinsically ergodic? Do you know if that has been studied?
Yeah. So there is this paper by I forget all of the authors. I know that von Klimenhaga was one of them. About like various conditions for intrinsic ergodicity by some modification of like specificity, I think. And it turns out that you can use this theorem that they proved to show that every S-graph shift and all of its vectors are intrinsically ergodic.
Is this paper called something like specification beyond intrinsic ergodicity beyond specification?
I think
Something
so.
like
I
that.
think
Yeah,
that's the
I know
one.
that one. Yeah.
Yeah.
Okay, cool.
Yeah, and so you can just use that result, and the proof is not so hard. It's just like a very simple application of this result, and it gets you the result.
Okay, nice.
Thank you very much. Do we have any other questions for Travis? Well, if not, I want to thank Travis and all of you for having come to the seminar. And it was a really nice talk. I mean, I have certain questions, but I think I'd rather read carefully the paper first in order not to be. But yeah, well, thank you very much. And I don't know if anyone wants to add anything.
Seems that no, it's not going to happen.
Well, thank you again. And I really hope you like your poster because
Yeah, it's a great poster.
Yeah, they put a lot of effort in the posters in here.
Yeah, thank you for inviting me. It was great.
Thank you for coming. Well, have an almost nice weekend, all of you.
Yeah, almost.